Hello everyone. So I'm Pajam Pauls. This is my colleague Alexander Treff, and we are PhD students from the University of Lübeck. And this is our joint work in progress called superVer, verifying probabilistic independence of systems of expressions using equality saturation. And we actually work in a quite different community. We work in security, hardware security, and cryptography. So a lot of terms that we use might be unfamiliar, and a lot of the concepts we use we'll try to explain high level. But if there are any questions in the end, please let us know if something was unclear. Then first off, the biggest change compared to the talks before is that the expressions that we will be talking about here are basically always probabilistic. We are interested in a different congruence relation than the one that we've been seeing before, which we always refer to as semantic equivalence in this talk, meaning that given an E-class, or given an expression, or given two expressions in this case actually, x, x or x, and 0, those two are in the same E-class, meaning that for each value that x can take, both they will always be equivalent. But in our context of cryptography, this is oftentimes not necessary. We only require a weaker notion of equivalence, which dictates that the probability distributions of two terms are identical. And for us, this would be enough for two terms to be in an E-class. And our goal is to use EGRAPHS, specifically EGG, to check for these probability distributions and compare terms in this way. And this also allows us to apply additional rules which are usually not possible in a semantic case, to apply simplifications that are in some cases a lot more powerful. Now, since we come from a security background, we have a different use case than some of the other talks before. We consider an attacker. And an attacker in our case receives a program, let's say an algorithm that is implemented, and this can be modeled as a circuit. So we can see here a bunch of different gates. What exactly they mean is irrelevant for this talk. But what an adversary can do is he can place probes inside the circuit to receive values from the computations. And the way that we can model these probes is by displaying them as algebraic expressions, which can then be evaluated to concrete values. The reason why we look at probabilistic expressions is because oftentimes these probes that an adversary can place also contain random variables. So for this reason, we go over probability distributions. And our goal is to perform verification. So what we want to do is, given such a circuit or an algorithm, we want to show that anything that an adversary can observe is independent of secret variables. Now, these can be freely annotated by a user. Any of these values could be secret or non-secret. It's very arbitrary. But the way that this verification works is, in a sense, if I give you two expressions and one of them contains the secret and one of them does not, if you are unable to distinguish them, if their probability distributions are the same, then we consider expressions to be independent of secrets. And what we have done is we have developed a tool in Rust that uses the EGG library to perform such a verification routine. Now we come to a very powerful probabilistic rewriting rule. This is called the optimistic sampling rule, also known as, or we'll refer to it as the opt rule from now on. And it was introduced by Barthe et al. In EGRAPHS24. And it states the following. So given a function that has a random variable and a bunch of other inputs, which are irrelevant for the actual function in this case, if, the probability distribution of this function and the random variable are identical if the following conditions are met. The first is R needs to be a uniform random variable. The second is the function that is displayed here needs to be bijective in that variable. And lastly, we see context again, but this is a bit different from what we've seen before. We say that R can only occur in this specific context of the function, meaning that all occurrences of the random variable are only in this same form. This cannot occur in two different contexts. And to look at a very simple example of such a function, given the random variable and a secret x, with the XOR operator, which is bijective, and we only have r once here, we can simplify this to the random variable r, per this rule. And this rewriting rule is oftentimes used in cryptographic algorithms to eliminate secret variables from the dependency and enable security against these forms of attackers. Now let's talk about how this rule can be modeled or implemented in EGRAPHS with a very naive approach. So given the example that I've just shown you, represented in just very simple E-classes, what we went with at first is we decided, okay, what if we want to maintain probabilistic equivalence? And we decide, given such an expression that can be simplified in this way, what if we just merge the two? What if we say the expression and the random variable have the same distribution, so we just merge them, they end up in the same class? Well, this brings us to the first question: how do we even determine inside an E-graph if an expression fits this definition of the opt rule or not? Since an E-graph can contain multiple different representations, some of them could allow for such a rewrite, while some of them would conflict with one. So what we do is we have used X analysis data to find such opt candidates, is what we call them, candidates for such simplification. And at a very high level, what this does is we look at the E-nodes that are created and determine if the operators that they use are bijective. And if this is the case, then we look at the children, the data of the children that the classes contain, or that the node points to, sorry. And we determine if conflicting contexts are found. If this is not the case, everything is fine, we can just propagate the data upwards. But if conflicting contexts are found, what we need to do is we need to sort of intersect over them and collapse them into each other to decide if representations can be found which have the same function everywhere. Sort of a choose function, I would say. If we can choose the same representation everywhere, we're okay. Then this is still possible. Otherwise, we need to discard the candidates. And whenever new candidates are found through different rewriting rules, we decide to update the analysis data by merging the old and the new candidates together through a union of candidates. And in order to lastly apply these rewriting rules, what we need to do is we need to look at the root classes, since these are the only classes which give us guarantees as to that no more conflicts are possible and anything that ends up in these classes are actual valid rewrites. This was very high level. If you're more interested in this, you can ask me again later. Let's look at an example where both semantic and probabilistic rewriting rules together are necessary to perform these simplifications. So given this example, we can see that the random variable r is only connected through a non-bijective operator, the AND, to another variable, which means automatically this discards it as a potential candidate for simplification. But what we know is that through the rule application of distributivity, we are able to rewrite this to such a form where the variable r is connected through an XOR to x1. And by sort of uncovering this representation and generating the new analysis data, we are able to determine that there is in fact now an opt rewrite possible on the expression r XOR x1, and then in the last step decide to merge these to eliminate x1 from the term. So through this chain of rewrites, we have determined that the first term is actually probabilistically independent from the term from the variable x1. And this leads us to a problematic example showing why this very simple naive approach is actually not enough. There can be problems with this. And it breaks down to two things. So the first is oftentimes in reality it is necessary for random variables to eliminate each other using the optimistic sampling rule. And by doing so, we oftentimes have the possibility to rewrite, to perform the same rewrite, to perform a rewrite on the same class using multiple different variables. So in this case, we can use both R0 and R1 to rewrite the original expression. And in performing this merge, some of you may already see where I'm going with this, the XOR now points to the same class for both occurrences, meaning that when we now want to perform the semantic rewriting rule, A XOR annihilation, which leads to 0 on the same class, we now have the problem that X determines that this is equivalent to 0. However, this violates the congruence relation which we had previously set, since 0 does not have the same probability distributions as multiple terms that are in this class. And therefore, this is not enough as an approach to tackle all examples that we would like to verify. Now, we have a fix for this, which my colleague Alex will now present to you.
All right, so our naive approach failed, as expected, I guess. But we have found a possibility how to circumvent this by introducing some kind of indirection into the EGRAPH. So we invented another type of class or node, which is the observation class, which only contains a special observation node. And these observation nodes are just pointers to other classes inside the EGRAPH, plus a potential sequence of opt rule applications. In this case, we have no application yet, which we denote by the bottom sign. So the observation node points onto the XOR class, and yeah, that's how we circumvent the total merge of everything here. And in the next example here, in this case, that's the very simple example from the beginning, where we have seen that we can rewrite X XOR R to R. So we can represent this as an additional observation node, which stores some kind of context that if we apply the rule in this order, then we can also point directly to the class containing R without merging the classes of the XOR into R. But in the observation class, we know that these two are equivalent. And so we can still work with this without merging the actual data. So here's a quick recap from the slide that we saw in the beginning. Just if you wonder why we call it observation class, because we're in this attacker context where the attacker can observe expressions. That's why we call it observation class and observation node. And if you look at this figure, you see two magnifying glasses. So until now, we only took the case where we consider one of these magnifying glasses, so one expression. And now in the next case, we want to see how to deal with systems of expressions, so multiple expressions at once. So for this, we have again this very simple example, and an attacker now can see two different positions in the circuit. One of them is it's just pointing on the XOR as before, and the other one is that he can also observe directly the value of R. And now we want to prove that the joint probability distribution is independent of secret. So up until now, the solution with the observation classes and nodes is fine. If we just consider an isolated expression, it's all fine. We can just pick one of the observation nodes and it's always correct. But now we have a problem again, because now we have to consider multiple expressions and consider them in total. So we have a local applied rule, the opt rule, but a global context that we have to consider. And that's where we get into problems again. Yeah, here we can see it. We can, by just applying the opt rule, again, generate a new observation node and merge it into the observation class from the first. But this is not valid in a global context, because they interfere with each other. If you want to give a simple intuition. The attacker can observe, if the attacker can only observe one of the two values at a time, then if he just observes X, or R, he doesn't know anything about the secret because it is masked by the random value. If he can only observe the random value, he won't learn anything either. But if he learns both of them at the same time, you can just subtract the R from the X, or R and he gets the secret. That's why we can't apply the opt rule here. And to solve this, we introduce something that we called realization analysis. And that's just simple enumeration of all possible observation nodes from the classes that we select, and then checking if they contradict each other or not. So the first two are always valid because we don't apply any opt rule. That's always fine, but it's not always optimal. So we can just iterate over all possibilities here and see which one is fine and which was not. So next case is we take again the first node from the first class, which just says we don't apply any opt rule. The second one says, okay, we replace R0, XOR R1 by R0. That's not okay. Why? Because the R0 is already also occurring in the first observation class, and we don't substitute the R0, R1. We don't apply the same substitution in the first class, so we're not allowed to do this. But we are allowed to do something different. We could, for example, substitute a term from the second class by R1. Why? Because the R1 is not occurring in the first observation class. But that's not the optimal solution. The next one is, it's the same as the first case, actually, or the first non-trivial case, where we again have a conflict because we perform a substitution with R0 in the first class now, but R0 is occurring in the second class as well, and we don't do it there as well, so that's not allowed either. That's the same case if we do that in the first, and in the second, this time we do another substitution, but they're not the same, so we're not allowed to do this. And then there is another case where we substitute X, XOR R0 by R0 in the first class, and R0 XOR R1 by R1 in the second class, which is allowed if you do the substitution in class 2 in first, and then in class 1. So you have to maintain the order. It's not allowed to do first the substitution in class 1 and then in class 2. So that's what we call a replay of rules. That's what context is in our case. Here's a small evaluation. We took other tools from our domain. We're not the best yet, but we're not shooting for any performance now, but more for correctness, because a verification tool that is not correct is useless. So first of all, if you see, Silver is a tool that is just trying out all possibilities with some optimizations, but it's quite slow. So as you can see, for the higher order cases, we don't even have results because it times out. If you Iron Mask, just doing some black magic, we don't know. And MaskVerif, the last tool, performs internally some observations that saves them one security order, more or less. We could implement something similar, but we didn't do it yet. And then I would say we could be in the same ballpark as MaskVerif. But we support B2A, which doesn't tell you anything, I guess. It's that's something. For now, we have seen the Boolean circuits, but you could also consider arithmetic circuits. And B2A is an algorithm to convert between those two circuit types. And this is becoming more and more popular, especially for post-quantum cryptography, where you do this a lot of times. So this is very relevant in our field of research. And to give you just an example of how simple this is for us, it's just a single line of code. There is a paper by Jean-Sébastien Gourjon who said, I proved that this complex expression can be rewritten as this more simple expression. He proved it by hand. And Pajam did his master thesis in our institute, and we said to him, can you just implement this rule in one of the other tools? And I would say it took weeks, months, I don't know. Yeah, multiple months. And for us, so we prepared the tests, we wrote this one line, 2 minutes later the test passed, and we're done. So the next steps now, as you can see, the state-of-the-art tools cannot verify all circuits that exist. There are more that they can verify, and we want to extend our tool to also verify those. That's one step, so to extend the functionality. And of course, to improve performance, now that we established correctness and completeness, we want to be a bit more performant. Because for now, we just build an EGRAPH for every system of expression again and again, which is not very efficient given that the expressions in such a circuit differ just by adding one more X or one more AND, etc. So I think we can hugely improve on this if we implement correctly. And of course, adapt domain-specific optimization techniques from other tools such as mask-verif. And then we maybe save a security order and step up one letter in the table, which would be nice. And yeah, that wraps it up. If you have any ideas how to improve, or if you know anything that where we reinvented the wheel and that's already something that we can use, just contact us. We would be happy to give to receive feedback and discuss things with you. Thank you.
Alrighty, thank you for the talk. We have time for maybe one question. I've got a question. So, you brought up basically what looks like a context node, and that's something we've been talking about a lot today. And one of the problems with these kind of nodes is if you have a large subterm if you have a large term with many subterms, and that term is in some context, you'll, for many reasons, want to sort of push down the context so you can see that context at every subterm level. Is that something you have to end up doing in your problem, or do these opt nodes live at the top level forever?
They live in the top node, in the top level forever. So we have this, I call it standard rewrites everywhere in the graph, and the probabilistic rewrites only happen at the top node to circumvent the problems that we had with our naive approach. So we don't push anything down again. Am I right?
All right, thank you so much.
Thank you.